Let's start talking about the Griffiths textbook. So Griffiths boils down classical mechanics just like this. And so we got Newton's second law. So let's say we're doing this in one dimension. Newton's second law is this. And of course, we can think of the acceleration as the second derivative of position versus time. And so what we have in Newton's second law is a differential equation. All right. And so in Physics 254 and other courses, what you can do is, given the force and then the initial conditions, so usually your position and velocity at, say, time 0, you can go through and solve this differential equation for your position as a function of time. And you can basically, in theory, figure out everything you need to about your particle and its future. In quantum mechanics, we have a similar equation. So this equation is the time-dependent Schrodinger equation. Now, just so you know, sometimes we'll call this the TDSE. So time-dependent Schrodinger equation. So it's a little more complicated than F equals ma, and we're going to spend the rest of the semester going through and dealing with this equation here. But it's really the same philosophy. This one sort of takes on the role of F equals ma for quantum mechanics. So given suitable initial conditions, usually we'll be given the initial wave function. One can, in principle, use this to solve the wave function for all time. And we'll see that this method for doing this is basically the same method we've been using for time evolution with our state vectors. And so the Schrodinger equation plays the role of Newton's second law in quantum mechanics. So this slide tries to summarize everything there is about our discrete case versus our continuous case. And the last video spoke about this in more depth. But in quantum mechanics, you're going to have primarily two different kinds of cases. One where to describe your state, there'll be different cases where it's a discrete possibility. So for instance, that's what we've dealt with so far. And so our state vector so far was some linear combination of, say, spin up in the z or spin down in the z. So the states that we could be in were discrete. There wasn't any in between. It was h bar over 2 or negative h bar over 2. But we're going to find in many cases, and the case first here, like with the wave function, is if I'm looking at some region from 0 to L where I might try to find my particle, in general, your particle will have a probability to be anywhere in that region. And so it's continuous. It can be at any point. It's not discrete like the spins were. And so the information then will be embedded in this thing here called the wave function. And so here's just a plot of your wave function psi of x. Now, these two things are different, okay, but they're very related, and we're going to try to draw analogies between them. So we'll spend some time doing that. And the one thing is, both of these things, so that's the state vector and the wave function, they're all we know about our system. And from them, we can get probability of certain things happening. In the discrete case, we could say Ca squared was the probability that our quanton would be measured to be in state A. And then we saw that, if you take Ca squared and Cb squared, it should be 1. And so that meant that it was normalized. Okay, so the total probability was 1. In our continuous case, it's going to be the same thing, taking the absolute square now of our wave function. Now this is where it's different. This is going to be a probability density, but it gives us very similar information. So here is our psi squared, the absolute square of our wave function, and this gives us information about where it's more likely to find our particle in this region. And so, for instance, this is the most likely spot to find it, and then maybe here on the sides, you're not very likely to find it. And in order for our wave function to be normalized, we've got this relationship here. All right, so in order to find a probability, we have to integrate this density over dx. And then if we go over all space from negative infinity to positive infinity, the probability of finding the particle somewhere should be 1. And so if we have this being true, then we have a normalized state. So this is how we normalize in wave functions. And again, that just basically means that we're 100% likely to find it somewhere. Griffiths talks about this, and so let's talk about it too. This is the really weird fact of quantum mechanics. So in classical mechanics, there's one kind of physical process, and that's basically things follow Newton's law. All right, well, here in quantum mechanics, there's two kinds of physical processes. And the first one is that the wave function evolves according to the Schrodinger equation. So again, the Schrodinger equation is kind of like the Newton's third law for quantum mechanics. And so that's the ordinary case. And then there's when there's a measurement, which everything sort of stops. The wave function suddenly collapses around one point, and then things again evolve according to the Schrodinger equation. This is really weird. This is probably one of the things that troubles most people about quantum mechanics. Now we're going to see that this ordinary will give us the time evolution rule. So we can justify a little bit where the time evolution rule comes from when we go through and further look at the Schrodinger equation. But still there's this issue between these two ways that things can go forward. And so Griffiths has a little picture sort of describing this where, before, if this is the probability density, it looks to be kind of like this here. So basically this has a probability of being at every point on my axis. And so this thing would evolve according to the Schrodinger equation, which generally means it could move around and do different kinds of things. The probability can switch around. But when you measure it, all right, you're going to find it collapsed around one point. And furthermore, if you measure it again, you're going to find it collapsed about that same point again, meaning that it can't change too much if you measure it really fast, sort of 2 times in a row. Our wave functions are going to be very similar to distributions that we might have looked at when we were maybe doing error analysis in first year. And so we're interested in some of the same things. One major thing we'll be interested in the average value. So for instance, the average value of whatever their distribution is measuring the position or the momentum. We're also interested in the spread, how widely distributed this is. And to do that, we're going to look at the standard deviation sigma. And so the definition for us for a nice bell-shaped curve here is that if I look over on one sigma to either side, I cover about 68% or about 2/3 of the values in my distribution. Now this is, not every distribution will be this way, but it's a pretty good sort of idea of what you're covering with that sigma. And so I thought would be good is Griffiths gives you a nice example, but let's actually go through one ourselves. And so we're going to work on this one together. And so it's the first 25 digits of pi. And so I've listed out the first 25 digits and how many there are. Like if you go through, there's 2 number ones, and there's 3 number 2s, so on and so forth. And so the first thing we want to do is we want to calculate the average value of the numbers in here. And so the way you do this is you make a sum of the number times the probability of the number. And so for instance, let's do this. So for the first one, it's number 1. The probability of number 1 is there's 2 of those out of 25. So then I add number 2, so that's number 2, and then there's 3 of those out of 25. Okay, and so dot, 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 if I go through and do this, and so you should do this and just sort of double check, I get 4.72. And so that's a 7, sorry about that. Here's my distribution, and so the average is somewhere, around in here, so it's basically thrown off a little bit by this. That's why it's not exactly at 5 or something. And so that's the average. Now, what you can then do is in a similar manner to this, all right, so we just calculated the average value of the number. Also calculate the average value of the number squared, right? And the reason for that is because that's going to be how we find our definition of sigma. All right, now that's the easiest way to find our sigma. Now our sigma is defined this way here. It's very complicated, but essentially, again, it's a number that gives you a sense of the spread. And what it's sort of trying to calculate is the average of how far every number is from the average. All right, and so do this, and then you can answer in the pre-class questions, and we can talk about this tomorrow.